Hello, this is Dr. Joe Trout from the physics program at the Richard Stockton College of New Jersey. In this lecture, we'll discuss Chapter 5, where we'll discuss air pressure. In the last chapter, we started with the first characteristic of the atmosphere, which was temperature. We started with temperature because most people can detect small changes in temperature. They can tell when it gets a few degrees warmer or a few degrees colder. Air pressure, even though it's very important to weather and the changes in the environment, is not easily detected by human beings. So a slight change in air pressure isn't detected as a slight change in temperature isn't as easily detected. So in this chapter, we're going to discuss the significance of the horizontal and vertical variations in air pressure. This is an element of weather that we don't physically sense as readily as temperature or even humidity. We'll start with the properties of air pressure and how it's measured, and then we'll discuss the reasons for spatial and temporal variations in air pressure. By spatial, we mean space, so how air pressure changes as you move east or west or north or south or up or down. And by temporal, we mean variations as due to time. So as time advances, how the pressure changes. So pressure is just force per area, and air pressure is just the weight of the column of air above us divided by the area. So just like someone standing on your shoulders, air pressure comes from the weight of the air that's above you. Air is a gas, and this gas is made up of molecules, and the molecules are in constant motion. And the air molecules collide with surfaces in a container and with the air. And the force of these collisions per unit area is the pressure. Dalton's law states that the total pressure exerted by a mixture of gases is the sum of the pressures produced by each of its constituent gas. So for example, the air pressure that you feel right now is due to the pressure from the nitrogen plus the pressure from the oxygen plus the pressure from the trace gases. Air pressure depends on molecular mass and the kinetic molecular motion. Don't forget we said temperature was a measure of this kinetic molecular motion or kinetic molecular energy. So air pressure can be thought of as the weight of the overlying air acting on a unit area. When we talk about weight, we're usually talking about the mass times the acceleration due to gravity, where the acceleration due to gravity is written as g, and it's equal to 9.8 meters per second squared. So the weight is equal to mg. So the pressure is the weight of that column of air divided by the area. The average sea level pressure is about 14.7 pounds per inches squared, or 1 kilogram per centimeter squared. Pressure acts in all directions. That's why, for instance, our houses don't crush in on themselves due to the pressure, because the pressure is acting equally in all directions. To measure pressure, we could use mercury barometer. And what this is a pool of mercury and we take a column of mercury that's closed at one end, and it pretty much looks like a test tube. We fill that full of mercury, and we invert that into that pool of mercury. That leaves a partial volume vacuum at the top, and the air pushes down, as shown by this red arrow, the atmospheric pressure, pushes down on this pool of mercury and pushes mercury up into this column. At sea level, the height of that column is about 29.92 inches, or about 760 millimeters. So that's 76 centimeters. As this air pressure changes that's exerted on this pool of mercury, then the height of the column of mercury will change. We of course have to make adjustments for the expansion of the mercury. So don't forget, that's how thermometers work, right? We heat the mercury and the mercury expands. We also have to look at gravitational variations with latitude and altitude. Why do we use mercury? Because you must know mercury's kind of nasty stuff, right? That's why the Mad Hatter in Alice in Wonderland was mad, right? It was from breathing in mercury vapors, which they used to use to make hats. So why use such a horrible substance? The reason is because if we were to use something like water, which is pretty dense, we would need about 33 feet of water. So we would need a column 33 feet tall. So any scuba diver knows every time you go 33 feet down into the ocean, approximately, you add another atmosphere's worth of pressure. So for instance, at 33 feet, you're actually at 2 atmospheres. And at 66 feet, you're at 3 atmospheres. So we use mercury because we only need 29 inches of it instead of 33 feet. We also have an aneroid barometer. And what that consists of is, in essence, a bellows-shaped balloon. And it's partially evacuated. And what happens is when the atmosphere pressure increases, we compress this balloon, and if you follow the linkage, the pointer goes high. And when atmosphere decreases, then the bellows move up, and the pointer goes low. This isn't as accurate as the mercury barometer, but it's a lot easier to carry around. We also use piezoelectric cells. So what that is a crystal, and when you apply pressure to the crystal, a voltage is produced. So what we see is that as the pressure changes on this crystal, we can measure that and figure out what the pressure is. You may notice that if you have a home use barometer, it might have things written like fair and change and rain. And these aren't to be taken literally, right? They're just approximations. But that does bring up one of the main topics in this talk. And that's, if you think about high pressure, think about fair weather. And if you think about low pressure, think about storms. So generally, if the pressure is increasing, we're going to see fair weather. And if the pressure is decreasing, we're going to see rain and storms. There's also a thing called a barograph, and what that is where we take the needle and attach a pen to it, and there's a cylinder that rotates with a piece of paper, and it records the pressure as time evolves. So for units of pressure, we can use millimeters or inches, and we explained why, right? The atmosphere can support a column 76 centimeters high of mercury. We also use pascals. A pascal is a Newton per meter squared. So sea level pressure comes out to be 101,325 pascals, or 101.325 kilopascals, so about 100 kilopascals. In the US, we use bars, and a bar is 29.53 inches of mercury. So a bar is about equal to the average atmospheric pressure. A millibar is just a thousandth of a bar. So usually worldwide the range is about 970 to 1040 millibars. The lowest pressure ever recorded is 870 millibars. The highest pressure ever recorded is 1083.8 millibars. Notice that the lowest pressure is during a typhoon, so Typhoon Tip in 1979. The highest pressure is in Siberia, where it was very cold. So as we move up through the atmosphere, the pressure changes, it decreases. So I'm sure if you've ever been up in an airplane, you probably feel your ears pop when you start to hit certain heights. And this ear popping is due to the change in pressure. So if we look at the sea level pressure, what happens is that all of the atmosphere above it is pushing down, compressing the air at the surface. So if it's compressed, then the gas molecules are closer together. And as we move up through the atmosphere, the pressure is going to decrease because there's less atmosphere above it. And there's going to be less compression as we move up through the atmosphere. This means that the spacing increases with altitude. So at 18 kilometers, about 11 miles, the air density is only about a tenth of what it is at sea level pressure, or at sea level. So because air is compressible, the drop in pressure with altitude is greater at the lowest troposphere. Then it becomes more gradual aloft. So if you look at vertical profiles of air pressure and temperature, we're going to base them on the standard atmosphere, and that's the state of the atmosphere averaged at all latitudes and seasons. So even though the density and the pressure drop with altitude, it is not possible to pinpoint specific altitude at which the atmosphere ends. So unlike the surface of the ocean, where we see where the water stops and the air begins, the top of the atmosphere, it's not so easy to see. It kind of bleeds away or fades away. We do know that half of the mass is below 5,500 meters. Don't forget, 5 kilometers is about 3 miles roughly. So half of the atmosphere's mass is below about 3 miles. 99% of it is below 32 kilometers or 20 meters, or 20 miles. In Denver, Colorado, which has an altitude that's higher than Boston, Massachusetts, the air pressure there is 83%, or 0.83 times the pressure at Boston, Massachusetts. So this shows the air pressure, how it varies with altitude. And notice that we started about 1,000, and at 11 kilometers, we're at about 300. So that was a change of about 700 millibars. If we now go up to 22, so we were at 300, we go up to 22, we're at about 100. There was only a change of about 200 millibars. So what this shows us is down in the troposphere, there's a very sharp change with height. But as we move up into the atmosphere, that change becomes more gradual. This shows a table of the standard atmosphere. And what happens is we're going to start off at a temperature of about 15 degrees, and it starts decreasing as we go up to the atmosphere and reaches about negative 50 at about 30 kilometers. This shows the pressure. So we start at sea level pressure, which is about 1,013 millibars. And at 30 kilometers, we're down to about 11 millibars, or 12 millibars. This next column, we like to look at the pressure compared to sea level pressure. Sea level pressure is usually written as P naught, and what that means is a P with a little 0 or O subscript. So if we look at the surface, the pressure at the surface divided by sea level pressure, we come out with 1. It's half of that pressure, so it reaches half of that value at about 5.5 kilometers. In this column we show the density, about 1.23 kilograms per meter cubed at the surface, going down to 0.02 kilograms per meter cubed at 30 kilometers. Once again, we have a column that divides the density by the sea level density. It's 1 at the surface. We reach half the density at about 6.5 kilometers. We find that actually horizontal variations in air pressure are much more important to weather than vertical ones. And we'll see that in a couple of chapters. Now if we look at weather maps, what we do is take a bunch of readings and we draw contours at connecting all the points that have the same reading. So these are called isobars. When these isobars close off, for instance here we have a low, and the isobars in the United States, we place them at 4 millibar segments at 4 millibar distances apart. So this is 1,004 millibars, 1,000 millibars. This would be 996 millibars, the one that's not shown there. Here we have a high, and if this is high pressure and this is low pressure, we'd expect air to blow from the high to the low. This is due to something called the pressure gradient force, and we can tell how great the gradient is by looking at the distance between these lines. So for instance here, we have a bunch of lines in a very short distance. That gives us a large pressure gradient. Here in that same distance, I don't have very many lines. There's not a great pressure gradient. Once again, the horizontal variations are much more important to weather forecasters than the vertical differences. So what we do is when we look at local pressures, they're usually adjusted to be equivalent sea level values. So for instance, if we take a pressure up at the top of a mountain, We'll extrapolate that down to sea level. And that's what we'll draw on the map. So this is going to show us the variations of pressure in the horizontal plane. And once again, these lines are called isobars. Horizontal changes in pressure can be accompanied by significant changes in weather. So in the mid-latitudes where we're located, a continuous procession of different air masses brings changes in pressure and weather. So temperature has much more of a pronounced effect on air pressure than humidity does. So in general, the weather becomes stormy when the air pressure falls, but clears or remains fair when the air pressure rises. So we want to look at the influence of temperature and humidity on air pressure. So if we have rising air temperature, that signifies a rise in average kinetic energy of the individual molecules. If we had a closed container, then heating the air would cause pressure to be exerted on all the sides. So it increased the pressure. So for instance, if you ever had a closed pot and you heated it, all of a sudden the lid would pop off because due to that increase in pressure. The density in a closed container can't change if the container is solid, right? Because we're not going to let any air molecules escape and we're not going to let any in. So the mass remains constant. And if the container doesn't change, then the volume remains constant. Therefore, the density of a closed container can't change. So if we heat it, the pressure is going to increase. The atmosphere doesn't act like a closed container. So heating in the atmosphere causes the air molecules to space themselves further apart. This is due to the increased kinetic energy. So the molecules are further apart, have a lower mass per volume or a lower density. So the heated air is less dense and lighter. And we're going to start talking about air parcels. Think of a parcel as a volume of air, so the same number, a constant number of molecules. So for example, let's take a hot air balloon. There the balloon has roughly the same number of molecules. And when we heat it, the balloon expands. And the balloon will keep expanding until the pressure on the inside equals the pressure on the outside. However, the density will decrease because the balloon has gotten bigger, but there's still the same number of molecules, the same mass of air in there. So now the density decreases and it moves up through the atmosphere. So when you think of an air parcel, think of an imaginary balloon that air molecules can't get in or out, but the volume of that balloon can change. The air pressure drops more rapidly in a column of cold air because cold air is denser and has less kinetic energy, so the molecules are closer together. As we saw, the 500 millibar surface represents where half of the atmosphere is above and half is below by mass. This surface is at the lower altitude in cold air versus warm air. Increasing the humidity actually decreases air density. You think the opposite would be true. You think water is pretty dense compared to air. If I put water into the atmosphere, it should become more dense, but it doesn't. This is why. Now, this is kind of a cartoon version of why, but if you think of nitrogen, in the atmosphere it's a diatomic molecule. These two large nitrogen molecules are stuck together. A water molecule is a large oxygen molecule and two little tiny hydrogen molecules. Well, if I force a water molecule into the atmosphere, it has to push a nitrogen diatomic molecule out of the way. So now these two large molecules are replaced by one large molecule and two little tiny molecules. So what happens is we actually decrease the density as you force moisture into the air. Now this is kind of weird because when we talk about really humid days, we say the air is heavy. Well, actually the opposite's true. However, we don't cool as efficiently in muggy, humid air. So for that reason, we say the air is heavy, even though the density actually decreases. So cold, dry air masses are the densest. They generally produce higher surface pressures. Warm, dry air masses generally exert higher pressure than warm, humid air masses. These pressure differences created horizontal pressure gradients, and the pressure gradients cause cold or warm air advection. By advection, we mean motion. So air mass modifications can also produce changes in surface pressures. So what we see is that local conditions and air mass advection can influence air pressure. During this semester, we'll talk a lot about diverging and converging. By diverging, we mean that wind's blowing away from a column of air. By converging, we mean that air is blowing towards a column of air. So diverging and converging are caused by horizontal winds blowing towards or away from some location. It can also be caused by wind speed changes in a downstream direction. And we'll talk about that in Chapter 8. So let's look at our hot air balloon. When air is heated, the air density usually decreases. So for instance, we take this balloon. It has a certain amount of air molecules. We heat those air molecules. It expands because the pressure is increased and the balloon can expand. It's going to expand till the pressure on the inside equals the pressure on the outside. But now the balloon is taking up more volume and there's still the same number of air molecules inside the balloon. So the density decreases because density is mass per volume. And the volume increased. So now the balloon is less dense than its surroundings, and it moves up through the atmosphere. So here we see a column of air. If there's diverging winds, so if the wind is blowing out from the surface, then other air will come down to fill in, which means we get convergence at the top. So if air is diverging at the bottom, it has to converge at the top. If air is converging at the bottom, it has to move up and diverge at the top. So these changes in air pressure are very important to weather. So we draw isobars are drawn on a map as we discussed previously. In the United States, we separate these lines in 4 millibar intervals. When we talk about a high pressure, we're talking about an area that has higher pressure than its surrounding area. If we talk about lows, we're talking about a place where the pressure is lower than its surroundings. So there isn't exactly a number that tells you if it's high or low. What we're saying is that it's high compared to its surroundings, or it's low compared to its surroundings. Rising air is necessary for precipitation to formation, right? So for clouds and rain to form. So what we have are lows, or columns of rising air, so they can go along the surface picking up moisture, if there is any, and then they get forced up into the atmosphere where clouds are formed. We've discussed the variability of temperature, pressure, and density, and these properties are known as state variables. So when we talk about the state of the atmosphere, we're talking about the values for temperature, pressure, and density. These three state variables are related through the ideal gas law, which is a combination of Charles and Boyle's law. And you've probably heard that the ideal gas law is PV equals nRT. If we divide both sides by V, what we end up with is that the pressure is equal to a constant times the density times the pressure. Times the temperature, excuse me. So it's equal to the pressure is equal to a constant times the density times the temperature. So if we hold density constant and increase the temperature, the pressure rises. If we hold density constant and decrease the temperature, the pressure falls. If we hold the temperature constant and increase the density, the pressure rises. So the density of air within a rigid closed column remains constant. So if we increase the temperature, then the pressure increases. Within an air parcel, which we said was a fixed number of molecules, so think of an invisible balloon surrounding a fixed number of air molecules, and the balloon can expand and contract. So the volume can change and the mass remains constant. So compressing the air increases the density because its volume decreases. Within the same air parcel, with a constant pressure, a rise in temperature is accompanied by a decrease in density. If we have expansion due to increased kinetic energy causes an increased volume, hence that at fixed pressure, the temperature is inversely proportional to the density. Okay, so we said the pressure was equal to the temperature times the density. If the pressure doesn't change and the temperature goes up, the density has to go down. Or if the temperature goes down, the density has to go up. This brings about the idea of expansional cooling. So when we have this air parcel and it moves up through the atmosphere and it expands, the temperature of the gas is going to drop. If we take this air and bring it down to the surface and it gets compressed, then the temperature is going to rise. So we have expansional cooling or compressional warming. Don't forget that we said the law of conservation of energy says that the energy can't be created or destroyed, only altered in form. So a change in internal energy is directly proportional to a change in temperature. If we compress a gas, we do work on the air. If we let the gas expand, we say that the air does work on its surroundings. The last thing we want to discuss in this lecture is an adiabatic process. During an adiabatic process, no heat is exchanged between the air parcel and its surroundings. So the temperature of an ascending or descending unsaturated parcel of air changes in response to expansion or compression only. So this is known as the temperature decreases in the environment at a rate of 9.8 degrees C per kilometer. We call this the dry adiabatic lapse rate. If it's moving through a moist environment, and it's moving adiabatically, that means no heat in or out of the system. Then we end up with the moist adiabatic lapse rate, and it drops about 6 degrees every kilometer. Once again, these are average rates. So, let's say we have an air parcel at 10 degrees near the surface. It goes up a kilometer, it loses about 10 degrees, and this is because of the expansion. So if expanded, the density's increased, the temperature's decreased. It goes up another kilometer, it's negative 10 degrees, it's expanded some more. So, as we move up through the atmosphere, we'll start at about 30 degrees. If there's no moisture, we'll drop at 9.8 degrees C per kilometer. If there is moisture, we'll drop about 6 degrees every kilometer. Once again, this is assuming that we haven't added any energy. So for instance, the sun isn't a factor here. So we're not adding energy and the parcel's heating up. This is just through moving up through the atmosphere and expanding, or moving down through the atmosphere and contracting. Okay, so we've covered so far two characteristics of the environment or the atmosphere. The first one was temperature. And temperature is a measure of the average kinetic energy of the molecule. And it's something we can feel even if it's just a few degrees change. And now we've discussed pressure. Pressure is the force per area. So the sea level pressure is due to the weight of the column of air above us. It's measured in millibars. And it's not as easily detectable as changes in temperature are. Okay, thank you for your time.